To the secret sharing session. The first talk is on traceable secret sharing by Dan Boneh, Arditi Partap, and Lior Rotem, and Lior will give the talk.
Can you hear me? Perfect. All right, so thanks, Yuval. So yeah, if we haven't met, I'm Lior. I'll talk about traceable secret sharing, and this is joint work with Dan and Aditi at Stanford. All right, so I'm sure secret sharing needs no introduction here, but just that we're all on the same page, saying that this is the first talk of the session. In secret sharing, we have a dealer that holds some secret S. It wants to split this secret among multiple parties, in this case 4, such that any T of the parties, in this example 3, can come together, pull their shares together, and reconstruct the secret S, right? So we have 2 properties here. One is correctness, that roughly says that any T shares should suffice in order to reconstruct the secret. And another is privacy, that, well, we have several ways to formalize it, but one of them is that the distribution over any T-1 shares is the same for all secrets, right? So this is just secret sharing. And secret sharing has many applications in cryptography and beyond. It's one of the most basic cryptographic primitives. One such application, maybe one of the most basic ones, is to just use secret sharing as is for secure storage, right? So as an example, think of Alice having her Bitcoin secret key. She doesn't want to lose it. She doesn't want to get hacked. So what she can do is she can secret share the secret key among multiple servers or storage providers, such that the correctness guarantee of secret sharing guarantees some sense of fault tolerance. So Alice only needs T of the servers to be online in order to use her secret key. And the privacy guarantee gives some sense of security against bounded collisions. All right, so this is a very straightforward application of secret sharing. Now, the question that we'll be interested in this talk is what happens if some of the servers, decide to sell their shares. So let's say that the first 2 servers come along, they put up a for sale sign, they pull the shares together, and if some adversary offers them sufficiently enough money, they just send over their secret shares. So yeah, so this is a very bad situation, obviously, right? It essentially reduces the threshold to 1, and even worse, this adversary can and might be one of the other storage providers, in which case all security is lost, and Alice lost all of her Bitcoin, right? So we want to protect against these kind of scenarios, and seeing that short of making physical assumptions, which you might do, but if we don't want to make any physical assumptions, we can't really prevent the servers from leaking their secrets or their shares. So what we want to do is we want to deter them from doing so, right? So one way to do that is if we get a hold of the leak, if we can trace it back to the servers, we can somehow punish them, take them to court, sue them, etc. And then hopefully this will deter them from leaking their shares, right? And note that without tracing, right, if we can't catch or direct the leak back to the servers who leaked it, then they have a risk-free incentive to just sell their shares, right? The secret key in this example might be worth a lot of money, so we need some sort of a counter incentive to deter them from doing so. All right, so this is the goal. And just before we get into specifics, just to convince you this is somehow a non-trivial problem to even formalize, note that we can't really assume that the shares are leaked as is, right? So if the shares are leaked as is, tracing can be trivial. So for example, think of a secret sharing scheme in which a share is just an actual share plus a message that says, I'm the share of party I, right? So obviously here it's very easy to trace. But if this is the secret sharing scheme, there's no reason for server I to actually leak the share as is. They can just leak the functional share prime, or even just change the index I to index J in the message, and then this will frame some other server, right? So we need some more general leakage model, and we need to be able to handle more general leakages than this one. All right, so this is the problem that we should have in mind. And with this in mind, what we do in this work is we consider the task of traceable secret sharing. So this was first considered in this conference 3 years ago by Goyal, Song, and Srini Vanasan. So what we do in this work is we have new definitions. Technically speaking, they're incomparable to those of GSS, but we find them to be natural. And we also have 2 constructions. So we have a construction that's based very closely on Shamir secret sharing. Essentially, we show how to trace leakage in Shamir secret sharing. And we have a construction that's based on Blakely secret sharing. So in both of these constructions, the share size is roughly the size of the secret. So it's just 2s, when s is the size of the secret. And this should be compared against the quadratic share size in GSS. Now, I should note that this is kind of an apples to oranges comparison, right? I mean, we have an incomparable definition. And in some sense, the gains in efficiency are also enabled by the different definition. But if you're really interested in having a practical share size and also tracing complexity, so I haven't defined tracing complexity, but hopefully this will become apparent in a few slides, then this change of definition and new constructions should really be come in handy. All right, so this is what we do. And what I'll cover in this talk are two things. So first of all, I'll cover the definitions. We have to know what it is we're trying to construct. And then very briefly, I'll give you the gist of the construction for Shamir secret sharing. Okay, and unfortunately, I won't have time to cover the Blakely-based scheme, but you can see the paper for that. All right, so what's a traceable secret sharing scheme? So it's just a 4-tuple of algorithms. You have share and reconstruct. These are your standard secret sharing algorithms. Then we have a trace algorithm that allows us to trace a leak back to the parties who leaked it. And we also have a verify algorithm that we'll disregard in this talk. Okay, we'll just focus on the tracing itself. So share will be the standard secret sharing algorithm, but with a twist. So typically, when we think of sharing a secret, we think of an algorithm that takes in n, t, and the secret s and spits out all of the n shares at once. Here, for definitional purposes, it will be more convenient to think of a share algorithm that samples shares marginally. So let's see how we do that. We get n, t, and s as before, but the share algorithm also takes in some correlation string, and you should think of that as the randomness that is shared across all shares, and some randomness R that is like the marginal randomness for the next share. Okay, and then it spits out one share, and also some component that will go into the tracing key that trace will get in order to trace. All right, so to give you some more intuition, in Shamir secret sharing, you should think of this correlation string as the random polynomial minus the free coefficient, so minus the secrets. Right, so everything is the same as standard secret sharing, except this correlation string and the fact that share spits out one share and the component for tracing key. So, the way we put this to use, just, so that we drive the point home, is we fix n, t, s and the correlation string once and for all. And then we sample the first share, we sample randomness. This gives us some share and a component for a tracing key. To sample the second share, we sample fresh randomness, but we keep the correlation string the same. This gives us a second share and a tracing key component, and so forth and so forth. All right. Reconstruct is the same as in standard secret sharing. It takes in t shares and outputs a secret. So correctness and privacy remain the same, other than the fact that now they should hold also over the choice of the correlation string. And also, you should consider tracer privacy, where privacy should hold, even if I give you the tracing key. All right. So this is like the basic syntax of secret sharing that we'll use. And now we can define trace. But before that, let's cast Shamir secret sharing in this syntax, since we'll use this later on. So the secret will just be a field element, like in standard Shamir. And the correlation string, as I mentioned, will be a random degree t-1 polynomial that passes through the origin. And so the ith share will just be Ri, where I is the randomness for party I. So it will be a random field element and the evaluation of G plus S on this field element. Okay, and the fact that this R is random will actually come in handy later on. So, you have your random polynomial. To sample one share, you sample a point. The share is this point, R1, and the evaluation of G plus S on R1, and so forth, and you can sample as many shares as you want. All right. So secrecy is the same as standard Shamir. The fact that we use random evaluation point shares is nothing, and reconstruction is also the same, right? You just do interpolation, and you find the intersection with the y-axis. All right, so we defined like the basic syntax, and now we can get into the interesting stuff and define what do we mean by tracing. So recall that we mentioned that we can't just assume that shares are leaked as is, because this is trivial and there's no reason to assume that. So what we'll do is we'll take after the trader tracing literature, and we'll model the leakage as a reconstruction box. So it has the leaked shares hard-coded in its belly somehow. We don't know how. And what it does is it takes in additional shares, in this case just one, because t is equal to 3, and it has two shares already, and it outputs some secret S star. All right, and we argue that this captures essentially any functional leakage or any leakage that's given sufficiently many additional shares will allow you to fully reconstruct the secret. All right, so any such leakage you can think of as an algorithm R. So now the goal, given access to this reconstruction box, we want to trace it back to the misbehaving parties. So let's be a bit more precise. R might have not just two shares hard-coded in it, but F shares for any F that's less than T, and then it will take T minus F shares as input, and we'll output a secret, and our goal will be to find the indices that correspond to the corrupted shares. All right, so with this definition of leakage, we can define the syntax of trace. So trace will take in a tracing key, TK. It will get black box access, to this reconstruction box R. We don't want to assume that we know anything about the implementation of R, so we just give trace Oracle access to it. What it can do, it can query R on tuples of shares, right? T minus F shares. And let's assume for these talks that trace knows what F is, but this doesn't have to be the case. And in the paper, it's not the case. And then it gets responses in the form of some reconstructed secrets. And the goal is to output some subset J that trace believes is the subset of corrupted parties. All right. So again, the goal is to trace this R back to the misbehaving parties. And more specifically, if the subset of misbehaving parties is J, so if it's less than T parties, and this R is good in the sense that it can actually be used in order to reconstruct the secret, and we'll formally define this in a second, then trace should actually find all of the leakers, and to avoid the trivialities, it shouldn't find any honest parties. All right, so this is the task. The way we formalize this, okay, so there's some glitch in the fonts, but the way we formalize this is through this following game. So the adversary specifies NT and subset J of corrupted parties. This J can also be chosen adaptively. Everything is symmetric here, so let's just assume that it's chosen at the beginning of the game. The challenger samples a secret and some correlation string, and then it samples N shares given this secret and correlation string. It sends the corrupted shares over to the adversary, who then needs to come up with a reconstruction box. And the challenger then uses trace in order to trace this reconstruction box back to some allegedly corrupted subset of parties, J prime. So we'll say that the adversary wins if this R is actually good. So now let's formally define what we mean by that. So if we sample T minus F additional shares and we give them to R, then with probability at least epsilon, R should actually output the correct secret S. So note that these shares are actually chosen with respect to the actual secret and reconstruction string, correlation string, sorry. So R has to be good. And in addition, the adversary needs to somehow avoid detection. So J prime needs to be different than J. So this means that either an honest party is blamed or not all of the corrupted parties are found. All right, so this is the security game. And the definition is that the secret sharing scheme is traceable if no efficient adversary can win this game. And just as a sanity check, let's see why we insist on J being less than T parties. Well, if it's not, then the adversary can just reconstruct the secret, and this R will also just output the same secret S, and this is independent of the subset J. So we have no hope of tracing. All right, so this is the definition. All right, so with this definition in mind, let's just see the gist of the Shamir-based construction. So as I mentioned before, or hinted to before, we focus on this variant of Shamir where the evaluation points are chosen at random. So this is for two reasons. First of all, it fits our definition nicely, but actually this is necessary. If you just choose the evaluation points deterministically, you can't hope to trace. Unfortunately, I won't have time to show you why, but you can see the paper for details. All right, so let's see the problem again. While we focus on the Shamir variant with random evaluation points. So now shares are just pairs. We have a field element and the evaluation of some low-degree polynomial on this field element. R, in this example, has two such shares hard-coded in it. It takes in an additional share, which is, again, a field element, and another field element, which is supposedly the evaluation of the polynomial at X, and it outputs some secret S. Right? When with that R, we need to trace it back to the first two servers in this example. So the high-level idea will be to do two things. So first of all, we observe that with some correlated queries, we can actually isolate the Lagrange coefficient of the point xy in the reconstruction of S. Okay, so if R is good, S needs to be the result of Lagrange interpolation of the corrupted shares and the input share. So we can actually isolate the Lagrange coefficient of xy in this interpolation. And secondly, we observe that if we have sufficiently many such Lagrange coefficients, well, this actually encodes the indices of the corrupted parties, and we can actually extract the indices of the corrupted parties from this encode. So this is the high-level idea. In the few minutes that I have left, I want to give you slightly more detail. So, if R is good with some parameter epsilon, sorry. Well, this means that with probability at least epsilon, S is the result of the Lagrange interpolation of x1, y1, x2, y2, and x and y, right? So these lambdas are just the Lagrange coefficients. Well, let's assume for now that epsilon is equal to 1. So this always holds, right? Well, what we can do is we can query R again with the same x, but a different y prime, and we'll get another Lagrange interpolation equation. So now we can rearrange and subtract. And what we get is that the inverse of the Lagrange coefficient that corresponds to x is y prime minus y over s minus s prime. Okay? And we can, extract this information because we know y and y prime, we chose them, and we also observed s and s prime from R. Well, what is this inverse of Lagrange coefficient? Well, we know what it is. It's just x1 minus x times x2 minus x over x1 times x2. So we get some equation in x1 and x2, and we have, the evaluation of this function at some point. So more generally speaking, for more than two corruptions, we get this equation. So the product of xi minus x over xi is equal to y prime minus y over s minus s prime. Well, what is this thing? The key observation is that we can view this equation as evaluation of some polynomial at the point x. Well, which polynomial? This h polynomial that you see on the slide. Right, so we get an evaluation of this polynomial h at the point x. So now we need to make two observations about this polynomial. The first is that it's a low-degree polynomial. It's of degree f, if we have f corruptions, because it's the product of f terms. And second, the roots of this polynomial are exactly the x values that correspond to the corrupted parties. Right, so you already see how this encodes the identity of the corrupted parties. So with this intuition, the tracing algorithm will just be the following. So the tracing key will be the x values that we assign to the shares, right? So this allows us to map x values back to the parties who hold them. And the tracing algorithm will just get f plus 1 evaluations of this polynomial. So for f plus 1 iterations, it will do what we saw on the previous slide. It will get an evaluation of this h polynomial. For sufficiently many such evaluations, we can interpolate the polynomial. We can factor it to find the roots, and then the roots correspond to the actual corrupted parties, right? And that's the entire trace algorithm for the case where R is actually perfect. So what do we do if R is not perfect? Or I should say that I implicitly assumed here that f is equal to t minus 1, but this easily generalizes to smaller f's. All right. So what do we do if R is not perfect? Well, the problem is that now S or S prime might be incorrect. It might not be the result of the Lagrange interpolation at the points that we're interested in, and we'll get a wrong H evaluation. So what we'll do is we'll note that if R is epsilon good, well, we should expect an epsilon squared fraction of the evaluation to actually be correct. Right, so we have a lower bound on the number of correct evaluations, and what you can do in this case, you can just use list decoding for Reed-Solomon codes, and we argue in the paper that you get a list of polynomials, but only one will actually match the tracing key. Okay, so you actually get a slightly more complex, but with the same idea, a tracing algorithm. All right, so let's just wrap up. We talked about traceable secret sharing. We saw one construction, and you can see the paper for the second construction. Now we can see that when I mentioned tracing complexity, I actually referred to the number of queries that we make to R. So if you use the Guruswamy-Sudan list decoding algorithm, you get f over epsilon to the fourth. Our Blakely-based algorithm is actually much better than that in terms of tracing complexity. We just need one successful query. And in terms of open questions, so the first is more applications, right? I mean, as I mentioned, secret sharing is a very basic thing that we know how to construct a lot of other primitives on top of. on top on. So, can we use this in order to get accountable threshold cryptography beyond just secret sharing? And the second is, well, we saw how to do, in some sense, tracing for Reed-Solomon codes. The Blakely scheme can be viewed as tracing for Hadamard codes. Can you do tracing for other codes, like CRT codes and LDPCs? And I don't have time, but if you want, I'll be happy to say offline as to why this is interesting. All right, so thank you.
Thank you. And maybe a quick question while the next speaker sets up.
During the talk, I was trying to map this to like a real world scenario. Say you're secret sharing like a signing key. So is the reconstruction box meant to capture things like the attacker reconstructs a secret and then goes and like signs a bunch of things it wasn't supposed to? Is that what R is, or is R something else?
No, so R in this case is a much more basic thing. It just gives you the secret, right? It reconstructs the secret in the clear and gives it to you. And somehow we actually use the fact that it reconstructs the secret in the clear, right? I mean, and not in the exponent.
So the attack is like someone publishes the secret somewhere, and you want to know who published the secret.
Someone publishes their shares of the secret somewhere, but they might sanitize them in some way or pull them together in some way that's kind of, to make detection harder, but still you want to fight.
Got it. Okay, thank you.
Sure.
Okay, let's thank Lior again. Okay, the second talk of the session is titled Towards Breaking the Half Barrier of Local Leakage Resilient Shamir Secret Sharing by Hai and Nguyen. And Hai will give the talk.
Okay. So it's good now. Okay. So let me start with secret sharing. It's a way to share a secret into shares so that any key shares can reconstruct the secrets where key is a reconstruction threshold. And if we lessen key share, then we cannot reconstruct the secret. So observe that this is a all or nothing corruption model. So what I mean is that the adversary either get full information or no information from every share. However, in the presence of side-channel attacks, this is no longer true. So the adversary can get some partial information from every shares. So in Crypto 2018, Ben-Hammad Degawa Ishai Rabin formally introduced this model. So in this model, the adversary can query independent leakage from every share and get back the leakage value from every share. And for example, if the leakage functions is a quadratic residue functions, then the adversary can know that whether each share is a quadratic residue or not. And now in this model, the security identifies if the adversary view is independent from the secret. And more formally, it is statistical distance between two leakage distributions is small. So in this work, we focus on Shamir scheme, and you have seen it in the previous talk. This is a polymer-based constructions. To share a secret S, it randomly pick a polynomial of degree less than the threshold, so that the evaluation at 0 equal to the secret. And shares are evaluations at distinct places. And in the picture, it is evaluations at x1, x2, xs. And why are we interested in this model? Because it has applications. So it is turned out to be a very useful primitive connect to other fields. For example, it's closely related to repairing real server codes. And this is a dual problem of liquid resilience. In this problem, the goal is to reconstruct the secrets using minimal information from every share. And it also have applications in liquid resilience MPC. Okay. And also, it's a modular building blocks for a lot of other cryptographic primitives. So in this work, we present two results, one positive and one negative. Let me start with the positive result. Okay. So the goal is to prove liquid resilience, and the smaller the ratio k by n, the better, where n is the number of parties and k is the reconstruction threshold. And we want to go below the half threshold for any arbitrary constants. And you can see here, the bounds get improved over and over, but it's still above the half threshold. And all of this works using the same framework introduced by BDIR 18, and they use linear Fourier analysis. And Massey et al. Show that if we use this approach, then there's no way to go below the half threshold. So if we plug in the quadratic residue liquid function I mentioned before, then the approach failed. It means that we proved the bar we get is not meaningful. And in crypto last year, Klein and Komarowski introduced a new framework, and they also use linear Fourier analysis. And with this, they can go below the half threshold, but for very specific local leakage family. That's the unbalanced leakage. So a one-bit function is unbalanced if it splits the domain into two sets of very different sizes. And they also improve the bound for all leakages and also balanced leakages. And note that for the QR leakage, it belongs to the balanced leakage family. So, so far, the best we know about the QR leakage it is 0.58. And in this work, we have very different approach. We use higher order Fourier analysis. So in the technical, I will explain what is higher order Fourier analysis. And using this framework, we can go below the half threshold. And actually, for any constants, the QR leakage in liquid resilience. And we can extend our analysis to deal with almost all local leakage. And here's it is almost all, but it's not all of them. So our result is an average K result. And for the worst K leakage, it remains open. And one remark here that in our analysis, we require that the field size need to be large compared to the number of parties, while all other works require some number of parties large, and it does not require P to be very large compared to N. And our results also extend to any MDS code-based secret sharing schemes. So for the attacks, let me summarize the prior work. In Eurocrypt 20, Nissan scheme present a randomized attack, and it can distinguish two secrets with probabilities at least half, as long as the number of bits used to represent the shares is less than t times n minus k divided by k. And this is a very general attack, but it's a randomized attack, and it's inefficient. And then work by Adam et al. And Maggi present an explicit and efficient attacks. It's called parity attacks. And this attack is good when the reconstruction threshold is small. And very recently, Konshuti, Tamo, and Buddha present an explicit 3-bit attacks that can determine the secret. And it works when k is of order square root of n, and the number of parties is equal to p minus 1. And actually, they study this in a different context in the repairing real server codes. And their goal is to reconstruct the secret. That's why the distinguishing advantage is one. And in this work, we make an improvement over the attacks. So we show that using only 2 bits, we can determine the secrets. And also we allow the number of parties to be linear in the field set. So we allow more flexible parameter setting. And the technical idea to put this, we use exponential sums and specifically the well-known wave-outs. And if you are interested in this, please take a look at our paper, or we can discuss it offline. For the rest of the talk, I will be focusing on giving some intuitions about our new framework. Okay, so here's our new proxies. So we show that the distinguishing advantage is bounded by summations over all the leakage values of the sums of a bunch of the Gaussian norms of balanced leakage functions. So here I show it for 1-bit leakage, but it works for multiple bit leakages. And you can see it have the Gaussian norms. So I will explain it later in the talk. The thing about it, it is some norm. And for the balanced leakage functions, it is different between 2 indicator functions of premises of the leakage. And our technical tools is to use higher order Fourier analysis. And in particular, we use Gaussian norms and generalized von Neumann inequalities. I will give more details about this. And using our proxy to prove the leakage resilience, it suffices to bound the Gaussian norms of a bunch of balanced leakage functions. So we use higher order Fourier analysis. So what is that? It is generalizations of linear Fourier analysis. And here I give a summary of both linear and higher order. So linear Fouriers have been around for a long time, and it studies how functions correlate it with a linear forms. And why higher order is developed very recently in mathematics. And this is very active research in mathematics. And it studies how functions correlate with polynomial phase. For example, quadratics or cubic. And both of them have found many applications in theoretical computer science. For example, probability testing, coding theory, learning theory, computational complexity. And one example of linear Fourier analysis would for counting linear patterns, but it can count only simple patterns. For instance, 3-term arithmetics. So 3-term arithmetics, it means the 3 numbers of the form x plus y and x plus 2y. And if you have a set A, that is a set of integers, then we want to count how many 3-term AP in that set. Then it captured by the expectations that you can see in the slides. And using linear Fourier analysis, we can count this quite precisely. However, it's not good enough to count some more complex linear patterns. For instance, 3-term AP. So that also the reasons in 1998, Gauss introduced Gaussian norms, and in the context of giving a new proof of the well-known similarity regularity lemma. And it counts more complex linear patterns. And this can be generalized to much more complex patterns. And it's called linear forms. So if we have a set of linear functions over t variables, and let's say every functions f1 to fn, and think about it, they are indicator functions, then the linear form lambda of size of f1 to fn is expectations over x times the product of those functions applied on the linear functions. And as you can see, for example, for the 3-term AP, it is in lambda of size of the indicator function of the set A. Okay, and for term AP, it is the same formula, but with one more indicator functions on the set A. Okay. So with that in mind, let me give you the main ideas of our approach. So the goal is to bound the statistical distance between two linear distributions. And we bound it by summation over all leakage values and a bunch of linear forms. And then we apply the heavy hammer from additive combinatorics. That is so-called generalized von Neumann inequality. And this is a key ingredient in the proof of a breakthrough result by Wintao in 2010. And intuitively, given a set of linear functions with some complexity D, and so we also have n function GIs, and think about that again, that is indicator functions. Then the linear forms is controlled by the D+1 Gauss norms of the functions. And the higher complexity D, then we need higher norms. So it's not very important to know what exactly is the Cauchy-Schwarz complexity, but in our setting, when applied for secret sharings, we can determine this number easily. Then applying this hammer extensively for every leakage value L and every indexes, we get the results. And let me give you an example. Consider n-parties and threshold k equal to 4 over Brown field 7 and with evaluation place 1, 2, 3, 4. And the basic fact tell us that the random set of the secret zeros here are linear codes, and it expands by the general matrix G0. And that matrix you can see in the slides. So from here, the first shares will be equal to x plus y plus z, where x, y, z are sampled uniformly at random from the finite field F7. And similarly, S2 equal to 2x plus 4y plus z. And so on and so forth. So now for intuition, suppose we'll consider QI leakage again. And let A to be the set of all the quadratic residues mod 7. Then we can rewrite the probability of leakage being 1 at the linear forms. And then the difference between the two probabilities can be written as the difference between two linear forms. But here we cannot directly apply the generalized von Neumann inequality because it's not exactly a linear form. But we can bound it by 4 different linear forms. And then you can see the balanced leakage function is showing up that is different between indicator of the set A and indicator of the set A shifted by the secret S. Okay. And then we get the results. And finally, as mentioned before, we need to bound the Gauss norms to complete the proof. Okay. So what is Gauss norm? So Gauss norms are defined over integers. So you have U1, U2, U3, and so on. So for example, if you look at U1, it's count the expectations over XA, fx times fx plus A. Intuitively, it counts the segments XA. Okay. And if you go to higher norm, and let's say it is U2, then it counts the number of parallelogram. And bounding the Gauss norm in general for arbitrary function is very challenging. And this is still very active research areas. But we managed to prove it for balanced quadratic linear functions using a classical results. And for random balanced linear functions, we use standard probabilistic methods. So to conclude, we developed a new framework using higher order Fourier analysis. And with this, we can go below the half threshold against almost all 1-bit leakage. And we present 2-bit leakage attacks that determine the secrets. And there's still a lot of open question here. The main question is, can we go below the half threshold for the worst case leakage? And what if the field size is not large enough? And can we extend the result to multiple bits? And also for attacks, can we do 1-bit leakage attacks? Or can we a text for the higher threshold regime. So that's all. Thank you for the attention.
Okay, we have time for one quick question while the last speaker sets up.
Do you think there is an easy way to generalize your analysis when it's not a deterministic function of the share that leaks, but rather a channel with eventually small leakages?
Very good questions. So in this one, we deal with the local leakage, and I'm not really sure we can generalize it to more general leakage model. Yeah, because we use the property of local leakage functions.
Okay, let's thank the speaker again. Okay, the last talk of the session is on stochastic secret sharing with 1-bit shares and applications to MPC by Benny Applebaum and Eliran Kahlon, and Eliran will give the talk.
Thanks. Can you hear me? Okay. Yeah, so this is a joint work with Benny. Okay. And in this work, we study a very basic question in secret sharing, the question of sharing a single bit using just 1-bit shares. And this question is motivated by the many applications of secret sharing almost everywhere in cryptography, for example, in cryptographic combiners, in private information retrieval, and of course, in secure computation. So for example, if you'd like to securely compute a Boolean circuit, then ideally what you'd like to have is a secret sharing scheme with just 1-bit shares. And a dream version of such a secret sharing scheme with 1-bit shares would be some kind of Shamir secret sharing, but over the binary field. Right, so we have a dealer, we have n parties, and the dealer wants to share a secret bit among the parties, and the first thing that we want is just 1-bit shares. Now, in addition, we'd like to obtain all of the amazing properties of Shamir secret sharing that are very important for the applications. For example, we'd like to obtain T privacy, so any set of T parties should have no information about the secret, but T plus 1 parties should be able to recover the secret. And Shamir secret sharing is linear, so we'd also like to have a linear secret sharing scheme. And this means that if we shared 2 secrets, SNS prime, and now each of the parties locally sums up the 2 shares, then these new shares actually define a secret sharing of the sum of the 2 secrets. And finally, just like in Shamir secret sharing, we would like this secret sharing scheme to be, this dream version to be multiplicative, let's say if we have an honest majority. And this again means that if we shared 2 secrets, SNS prime, and now each party locally multiplies the 2 shares, then we can still recover the multiplication of SNS prime given all of these multiplications of the shares. Right, so this is the dream version, achieving 1-bit shares together with all of these properties. However, there is a problem, and the problem is that Shamir secret sharing requires the size of the field to be larger than the number of parties. And therefore, even if you have just 1-bit secrets, the share size is still log n bits. And in fact, we know that this is inherent. So in every threshold secret sharing scheme, the size of the share has to grow logarithmically with the number of parties. So it turns out that this dream version is actually impossible. So as a second best, and to reduce the share size, previous works considered the relaxation of a threshold secret sharing that is called ramp secret sharing. So here again, we require privacy against any set of T parties, but now there is some gap between the privacy and the correctness. So instead of requiring T plus 1 correctness, we just require T plus epsilon n correctness, where epsilon is just a small constant. And we know how to construct ramp secret sharing from linear error correcting codes. So there is a transformation that takes linear codes and transforms them into ramp secret sharing.
the distance of the code is translated to correctness. And in order to get a good privacy, what these codes need is a good dual distance. And these constructions are in fact linear and multiplicative, which is again very important for the applications. And in addition, they achieve a constant share size. So the size of each share is just a constant number of bits. It's log of 1 over epsilon, and epsilon is just a constant. All right, so we paid a little bit in this gap between the privacy and the correctness, but in return, we got a constant share size. However, there is still a problem, and the problem is that if we insist on having just 1-bit shares, then the gap epsilon has to be very large. It has to be at least a third. And this means that the best you can hope for is something like a T privacy and a T plus N over 3 correctness. And in fact, in existing constructions, the situation is even worse, and this is not good enough for the applications. So we remain with this question of having a secret sharing scheme with just 1-bit shares. And we've seen that we cannot use threshold secret sharing or ramp secret sharing. So we ask whether there is some notion of secret sharing that would allow us to obtain 1-bit shares. And we want this notion to be meaningful, which means that we want to obtain these nice properties of Shamir. We want it to be linear and multiplicative, so that later we will be able to use it in other areas of cryptography, for example, in secure multi-party computation. So in this work, we answer this question. We show that the answer is yes. I'm going to present 2 new notions. The first one is stochastic secret sharing, where we have probabilistic corruptions. Then I'll talk about static secret sharing, where we have standard worst-case corruptions. And finally, I'll talk about applications to MPC. Okay, so let me start with stochastic secret sharing. And in stochastic secret sharing, the parties are corrupted according to the stochastic corruption model. So every party is corrupted with probability P independently of the other parties. All right, so for each party, we toss a coin. This is a biased coin. It is 1 with probability P. And if we got 1, then this party is corrupted. And we do the same thing for the second party. And if we got 0, then this party is honest. Okay, so the set of corrupt parties is not chosen by the adversary, but rather it is chosen according to this simple stochastic process. And I want to mention that stochastic corruption model already appears in cryptography, for example, in leakage-resilient circuits, where every wire is linked with probability P, and also in cryptographic combiners. Okay, and now in stochastic secret sharing, what we want is that with very high probability over the choice of the bad parties, again, according to the stochastic corruption model, we have correctness, which means that the honest parties can always recover the secret. So whenever the dealer shares a secret among the parties, the honest parties alone should be able to recover the secret, while the corrupt parties should have no information about the secret. Okay, so again, we require, in other words, what we want is that with very high probability, the set of honest parties will be an authorized set that can recover the secret, while the set of corrupt parties will be an unauthorized set that has no information about the secret. So this is the definition of stochastic secret sharing. And it's not hard to see that the corruption parameter P cannot be larger than 1/2. And our first result is a construction of stochastic secret sharing with just 1-bit shares for every constant P that is less than 1/2. The error is a sub-exponentially small in the number of parties. Our construction is linear and multiplicative, which is what we wanted. And this is in fact a very simple construction that is based on the Reed-Muller codes. Okay, so here it is. We have a dealer, we have n parties, and we said that the dealer wants to share just a single bit. And from now on, we work over the binary field. So to share this bit, the dealer picks a random polynomial whose free coefficient is the secret. But now this is a multivariate polynomial with the m variables, and the degree is the m over 2. Okay, m is log n here. And the shares are just the valuations of this polynomial. Okay, so this is the secret sharing scheme. You can see that shares correspond to a Reed-Muller code word. And yes, this is our construction. So we can construct stochastic secret sharing with just 1-bit shares that is linear and multiplicative. And again, we have a very simple construction, especially if we compare it to other explicit constructions, like those that are based on algebraic geometric codes. And to analyze this construction, we have a new technical lemma that extends known relation between linear codes and secret sharing. So just before explaining the statement here, let me remind you what is the binary erasure channel. So the binary erasure channel with parameter P takes as an input a code word. And it outputs the same code word, but where every coordinate is erased with probability P, so you can see that the output has some erasures. And we say that the code behaves well over the binary erasure channel if given the output, we can recover the input, the original code word, to very high probability. Okay, so this is the binary erasure channel, and what our technical lemma says is that if you have a linear code that together with the dual code behave well over the binary erasure channel, then you can transform it, then you can transform them into stochastic secret sharing with the same corruption parameter P. And now to obtain the first result, we use the fact, this is actually an amazing fact, that read-monger codes achieve capacity over the binary erasure channel. So both a read-monger code and its dual, which is a read-monger code, behave well over the binary erasure channel, so they imply stochastic secret sharing. Okay, so this is our first construction. We have an alternative construction where we use the fact that random linear codes also achieve capacity over the binary erasure channel. And this gives us a probabilistic construction of stochastic secret sharing with just 1-bit shares, again, for every constant P that is smaller than 1/2. The error now is exponentially small in the number of parties. This construction is linear, but it is not multiplicative. And in fact, using the techniques of Druck and Ishai, we can even obtain a linear size circuit. Okay, so to compute the shares, you can use a circuit of size O of n, which is very efficient. Okay, so those are the results regarding stochastic secret sharing. And next, we'd like to obtain some kind of security, even in the standard corruption model, where the adversary can choose which parties to corrupt. So here again, we have a new model, we have a new notion of static secret sharing. So we have a threshold T, this is the number of corrupt parties. And we have public randomness. And here is the game. So first of all, the adversary chooses which T parties to corrupt. Then we generate a public randomness. And now the public randomness fully defines the secret sharing scheme. So it tells the dealer how to share a secret, and it tells the party how to recover the secret. Okay, so the adversary is static. The first thing that happens here is that the adversary corrupts the parties. And the definition requires that for every set of T corrupt parties, so again, the adversary is static. First of all, we fix the set of corrupt parties. With very high probability over the choice of the public randomness, we have correctness, so the honest parties can recover the secret. And we also have privacy. So the corrupt parties should have no information about the secret. And again, this means that the set of honest parties is an authorized set, while the set of corrupt parties is an unauthorized set with no information about the secret. And I do want to emphasize that static secret sharing is a strict relaxation of ramp secret sharing, because here we require both correctness and privacy only with respect to a specific set of T corrupt parties. While in ramp secret sharing, we require privacy, for example, for every set of size T. Okay, so this is a weaker notion than static secret sharing. And I also want to mention that the public randomness is chosen just once, and you can use it many, many times in many instances of secret sharing. So the public randomness does not affect the amortized communication complexity. Now, to construct static secret sharing, we show a transformation from stochastic secret sharing to static secret sharing. So we start with the p-stochastic secret sharing with error delta, and we transform it into a static secret sharing where the adversary can corrupt p fraction of the parties, and the error grows to 2 delta. And the transformation is actually very simple. All we have to do is to permute the parties. Okay, so here is the main idea. First of all, the adversary chooses which T parties to corrupt. And then we generate a public randomness, which is just a random permutation of the parties. And now to share a secret, the dealer uses the original stochastic secret sharing scheme, but with respect to the permuted parties. So the first party receives now the share of pi of 1, the second party receives the share of pi of 2, and so on. Okay, so this is the new static secret sharing scheme. And the idea is that we first let the adversary to corrupt p fraction of the parties, and only then we take the permutation. So essentially, we force the adversary to corrupt the random p fraction of the parties. Right? And this is very similar to the stochastic corruption model, so stochastic secret sharing still provides security in this case. Okay, so this is the transformation, and now we use this, our constructions of stochastic secret sharing and transform them into static secret sharing. So we have a construction either from read-monger codes or from random linear codes with the same parameters as before. Okay, so this construction is the optimal communication in the sense that every share is just 1 bit. And I'll say that we have a more sophisticated transformation that allows us to have amortized linear size circuits. So if you want to share a secret or to recover a secret given on the shares, you can do so using a linear size circuit, a circuit of size of n, which is again very efficient. Okay, so this is not part of the paper. We hope to publish a short note with the full details in the soon. Okay, so those are the results regarding static secret sharing. And finally, we use static secret sharing to construct a communication efficient MPC. So we construct a statistical MPC for Boolean circuits. It is secure against a passive static adversary that can corrupt a minority of the parties, essentially every constant fraction being 1/2 of the parties. Our protocol has an offline phase that depends only on the size of the circuit, where each party communicates a number of bits that is linear in the size of the circuit. But then in the online phase, where the parties actually compute the circuit, each party communicates just 1 bit per gate. Okay, the total communication is therefore n times the size of the circuit. The error is a sub-exponential in the number of parties, and in fact, we can even implement the parties very, very efficiently, either in the RAM model, or if you use this short note that I've mentioned, we can even implement each party using only a linear size circuit. Okay, so this protocol is very efficient. I've said that there have been many, many works on the communication complexity of information theoretic MPC. Those are just some notable examples. And the state of the art, which is the last work here, achieves communication complexity with only logarithmic dependency on the number of parties, together with perfect security with no error. And I've said that we can improve our results using standard techniques, essentially by picking a random small committee to execute the protocol, and also obtain a logarithmic dependency on the number of parties and still maintaining a negligible error. So we are not too far from the state of the art. And in addition, our protocol has some nice features. So first of all, it is a very simple protocol. We follow the gate-by-gate paradigm with standard optimizations. And second of all, we do not require any pre-processing of the circuit, while many of the previous works do require a pre-processing of the circuit, so they require knowing the whole circuit at the beginning of the execution. And for this reason, our protocol supports the real-time model, so let me explain what it is. So in the real-time model, in each step, you get a bunch of instructions, and the parties need to securely compute the output. But now the next set of instructions might depend on this output. Okay, so you don't know what future instructions may be, because they might depend on intermediate values that the parties computed. And in the paper, we show some examples where the real-time model occurs naturally, for example, in the secure computation of binary search. And we even show that in this case, we can obtain a communication complexity that is sublinear in the circuit size. Okay, so in some cases, you do want to use the real-time model. So let me conclude. We've discussed stochastic secret sharing. In the stochastic corruption model, we've seen a transformation from linear codes that behave well over the binary erasure challenge to stochastic secret sharing, and use it to construct stochastic secret sharing with 1-bit shares. We then discussed static secret sharing. We've seen this transformation from stochastic to static and use it to construct a static secret sharing with 1-bit shares. And finally, we discussed applications to MPC. We've seen the secure computation of Boolean circuits with honest majority, where in the online phase, each party communicates just 1 bit per gate. And finally, I've discussed this real-time model. Thank you.
Thank you. Any questions? Yes.
Thank you for the talk. So I was wondering if this stochastic secret sharing or statistic secret sharing can be made pairwise verifiable.
What do you mean?
Like in Schmidt secret sharing, you can introduce bivariate polynomial to make them pairwise verifiable.
Yeah, that's a good. I'm not sure. Yeah, I'm not sure. But it will be useful for verifiable signature.
Okay, we have time for more questions. Maybe I'll ask, what about the packed version? Because if you have strictly less than 1/2, you can actually hope to boost the efficiency by using, basically you can get constant rate. Instead of sharing 1-bit secret, you can hope to share omega of n bits.
So could you repeat the question?
Yeah, I'm saying that if you have a rate which is strictly less than 1/2 corruption rate, then you can hope to share a secret of size omega of n with 1 bit per share.
So I don't think so. I don't think that we can get to.
With some gap. But if you have, say, P and P prime, two thresholds for secret sharing construction.
I'm not sure. At least in the construction of Friedman codes, I think that the best you can hope for is something like the square root of n.
Okay. Okay, let's thank Eliran again. So we have the ICR business meeting in 5 minutes in this room.